we have kind of hit the point in calc where we are pretty much summarizing everything. So the fundamental theorem of calculus is the summary of derivatives and antiderivatives kind of put together. So what's crazy though is we actually always start with part 2 of the fundamental theorem instead of part 1. So whoever numbered these back in the day numbered them backwards. So we're actually going to start with the second fundamental theorem of calculus instead of the first today. So what I want to do is go back to the very beginning of chapter 5. How did we start chapter 5? Riemann sums. So in order to understand the fundamental theorem of calculus, we're going to understand it by starting at the very beginning, how we started. Riemann sums. So sketch the region whose area is given by the antiderivative of 2 to 5 of 3 plus 2t dt and the region whose area is given by 2 to x of 3 plus 2t dt. So go ahead and sketch your region. So again, we're going from 2 to 5. So if you had 2 plugged in,
Yeah.
we're just talking about this region. Okay, let's actually antiderive it. So antiderivative here. So again, you plug in to your antiderivative. So 5 times 3 is 15. 5 squared is 25. 2 times 3 is 6. 2 squared is 4. But remember, it's f of b minus f of a. So you have 15 plus 25, which is 40. 40 minus 10 gives you 30. So looking at your region or your space, we know that that's our goal, or that area under the curve should be about 30. So that's what I was saying, where you kind of drew in your trap. You sketched this, but it said sketch the region whose area is given by that. So what were you actually trying to sketch? You were actually trying to sketch the quadratic, which meant you had to plug in, yes, your endpoints, which was why I said mine was kind of flatlined at 10, because I was plugging in the endpoints of my antiderivative. just trying to sketch the region whose area is given by that. So the area we got is 30. The area of that region would be 30. Then it says, and we have 2 to the x. So that x is kind of like anywhere. We don't really know where x is. So the idea is that we could go backwards and sort of find this unidentified x. So x itself could live here. X could live here. X can kind of live wherever x wants to live. So what we want to do is show that by differentiating 3t plus t squared, we get the antiderivative of 3 plus 2t. So could you see that if you took the derivative of this, we would get that? Yeah? I mean, that's pretty easy for us, right? So this is kind of like saying, all right, capital F of x is equal to 3t plus t squared. So lowercase f of x would equal 3 plus 2t. So we understand that connection. Now, what we're going to do is this idea of FTC to find an expression for 2 to the x of 3 plus 2t dt. So, that's where we're going. This is kind of like our goal. We're going to go back and fill this in after we do some of the notes, because we don't know what FTC is just yet, but we're going to go back and make the connection to all 3 of these. If I asked you this, what is the derivative of the antiderivative of 3 plus 2t dt? Okay. What's this variable and what's this variable? X. So, when you antiderive, your variable changes. So if you take the derivative of an antiderivative, and these are x's and that's t's, your variable will change. And we're going to see why through this. And you're going to see where that x on my board in purple comes into play too.
So you would derive it and have t's and then you could
You would plug in f of x minus f of x. Exactly. So, and that's what we're going to look at. So why would this change to an x, and how does it change, and then how does this relate to all of that? So it's kind of like the warm-up takes us back to the problem at the very end. So, just thinking in terms of integrals, if you have f of x equals x cubed plus cosine x, you can't see the top. Oh. It's okay.
Whoa.
It'll all be good. I'll make it big in a minute. It's just that was too high up.
Yeah.
What's the indefinite integral for this function?
1/4 x to the 4 plus sine x plus c.
Good. Good. So again, the x cubed became 1/4 x to the 4th. Antiderivative of cosine is positive sine, and he led or ended with his plus c. I asked you to find the derivative of this integral. What's the derivative of this? So you can see the forwards and backwards motion. You want to see how big it is?
Oh.
Look how gross my handwriting looks big.
That's so weird.
What?
Oh my. Yeah.
That's what it records. So like he doesn't see this, and he didn't see me like you. Okay. Fundamental theorem. let's talk about it. It says if we have lowercase f as our function, and it is continuous from A to B, then capital F of x is equal to the integral from A to x of f of t dt. Is an indefinite integral of the antiderivative of f. And that's the key. That when we have bounds, we call it a definite integral. But because we have bounds with a variable, instead of bounds with a constant, it goes as an indefinite integral. We can say then that the derivative of f prime of x would give you f of x, not f of t, f of x. If f was the definite integral from a to b of f of x dx, then we have our f of b minus f of a. So we're going to see how this theorem presents such a connection between derivatives and antiderivatives. So let's talk about it. The theorem presents this astonishing connection between differentiation and integration. So again, today is like the all-encompassing day of let's bring everything together. If f is continuous on the closed interval ab, then the function capital F of x from a to x of f of t dt has a derivative at every point x in the closed interval ab, and f prime of x equals df dx, or the derivative of the integral. So this is where the two parts are going to come into play. We're actually going to kind of rip this apart and look at one part and then look at the other. So there are two parts to this theorem. Since this is so important and since this is such a huge concept, we're actually going to go through the proof of it. It's not terrible. How much space did I give you?
Pretty good enough.
Yes, well, my three big handwriters, I would still write small. It's about 9 lines. Okay. We have to start with a let's statement. So let's start with a statement of this. Let's start by saying capital F of x is our antiderivative from a to x of f of t dt. Our goal, or what we are trying to prove, is that f prime of x is equal to f of x. That's what we're trying to prove. That's our end goal. So if we're trying to prove f prime is equal to f of x, what do I probably need to start my proof with? What do I probably want to start with? Yeah, I want to find f prime, right? So how do you find f prime? What do I need? I need to take the derivative. But let's go back and talk about what was f prime of x equal to way back in the day. What was the very first way we learned about derivatives? Yeah, the definition. So by definition, f prime of x is the limit as h h approaches 0 of capital F of x plus h minus capital F of x all over h. That's where we started. How could I relate this to that? This is f of x, right? So that could go in here. Do you see how this piece represents f of x? So what could I do to represent f of x plus h? What would change? If this represents f of x, x plus h would just change my upper bound. Is up there? Do we see the connection? See how this is capital F of x, and that's equal to this, so all I did was substitute the integrals in. So this is definition of the derivative. This was substitution. What do we know, or what could I figure out from here? Perfect. So, do you see what he said? See how these have the matching A's? I need the A's to match up in order to combine the integrals. So what he said is, if I change one so that the A is negative and at the top, then I can group them together. Okay? I'm seeing some. Great. So, like, since I want this A to be up here, I could minus the minus, which would flip that, so that I would go A, well, I mean, yeah, x to A, and then A to A plus x plus H. Do I need to write it out, or are we okay? We kind of understand like what we're talking about.
Right now.
Let me run out of board space. So the rule is that you can add integrals if they match. So the way it is right now, I have an A to B and I have an A to C. So we're subtracting them. What we want is we want to match them up so that the A's go from one to the other. So you could rewrite this or think of this as negative A to C plus the integral from A to B. But what I want is I want the C to be down here and the A to be up there.
So you end up. So then you can.
So then you can take a negative, exactly.
So you end up with the integral from C to B.
Yes, eventually. So now it's like C to A because I took the opposite. So now my A's align. So my new integral is C to B and the A's kind of go away. So the C in that case is x, and the B in that case is x plus h. So this is going to go from x to x plus h of f of t dt all over h. What does that kind of look like?
The mean value.
Not mean value, but the other one. We don't call it mean value, we call it the average value. Yeah. This looks like the average value of the function. Do you not see it? So right here, can you see that this looks like the average value of the function? What does the h represent? Exactly, it would represent what we used to call b minus a, but if b is x plus h, and you subtract x, what do you get? H. So can you see how this is the average value function that we talked about on whatever day that was, Tuesday? Alright. So, if that represents the average value function, we're going to use the average value function to guarantee myself what? That there exists that point in the rectangle whose area matches the 2. So, that's what we're going to talk about next. So we have the average value of the function. We said it's from x to x plus h. So that leads me into the mean value theorem. So you were like kind of thinking ahead, Michael, when you gave that suggestion. So by the mean value theorem, and then here's what's important. You have to now say by for integrals. When you say MVT, they assume derivatives. If you want to use MVT for integrals, you have to use the words for integrals. You don't have to say MVT for derivatives when you use it for derivatives, but you do have to say for integrals when you use it for integrals. So, by the mean value theorem for integrals, what are we told? Well, we're told there exists at least one point C in that closed interval this limit now equals f of c. So it's saying that f of c has to equal that limit. And I'm going to pull my 1 plus h out here. Oh, I lost the word limit. Okay. So we're guaranteed this by MVT. Okay. Oh. Okay, so this represents f of c. There is no limit on this part. The limit's part of the other definition, which is that f prime of x equals the limit. So this, that's what I just can't see on my page, right? So that's what we know about f prime. This is what MVT tells me. So where can I make a substitution in again? Do you see how this can get replaced by that? So MVT guarantees this f of c by the average value function. So that means that f prime of x would equal the limit as h approaches 0 of f of c. Where c lives in this closed region. What's the beginning of the closed region? It's an x, right? Wouldn't it be fair to say then that since c lives in x to x plus h, that if we plugged x in here, f prime of x would have to equal f of x? Because we know that f of c lives in x to x plus h. So what's the connection? What's the big idea? Well, the fundamental theorem of calc uses the average value of the limit of the derivative. So the idea or the concept, what we're taking away from that, has to do with inverses and the relationship between differentiation and integration, or antiderivatives, or antidifferentiation, and the respect they have to their inverses. So they're inverse operations of each other. It's kind of like saying 2 times a half is 1. The derivative of the antiderivative is the original. That's what that's saying. The derivative of the antiderivative is the original. The derivative of the antiderivative is the original. From this, we can say every continuous function has an antiderivative. We can also say that every continuous function f is the derivative of some other function f of x. This is literally like they call it FTC. I call it, let's just say that when you get a problem that says using the fundamental theorem of calculus, you're just kind of plugging in bound. Why did you handwrite those on? Are we good? It's hard to tell like when we're done and like not done. Ceiling lighting a little isn't necessarily faster. I'm kidding.
Yeah, I finished late first.
However, hold on. Could you read his notes, Nathan, if I told you you had to trade with him?
He can. I can translate some of them.
I can translate some of that.
Oh. That's actually better than mine, I think.
Oh, I think his handwriting's improved way more than yours has. Like, if I would take out, like, a paper from when you guys were sophomores, yours is probably still very similar.
Yeah.
Michael's has improved a ton.
It's sad that I can read this because there's a lot of wrong like spellings, like they don't look like a letter. But I can assume what the letter is from the rest of it.
Can you read this? That's your.
Oh, Anthony, you're gonna have to fix your handwriting for the AP test because if you write how you write,
Like
your
this,
one class that I graded, I actually almost gave you no points because I couldn't read it.
Wow.
And I had Mrs. Volanich try to read it, and she couldn't read it. And if you do that on the AP test, they're gonna push it aside because if it takes them more than like so many seconds to like grade a paper, they say nope, we're done. Come on, you're not the most recent quiz, and not the PIT quiz. The quiz that was right before that, the related rates one, where I made you like write out like, something at the bottom. It said like explain like what's happening with the balloon, and I was like,
I'm pretty sure it was like low in time.
I took like a picture and tried to like zoom it in because it was so tiny and so hard to read. I was like, what? I can't read this. I literally was like, I almost texted you to like come back to my room and try to read it to me. All right. So, FTC says find the derivative of an antiderivative. Find the derivative of an antiderivative. So, dy dx in this case is simply equal to all of this, but everywhere you have a t, you now have an x. The derivative of the antiderivative is all of that, And everywhere you go t, you have an x. No plus c. That's key. No plus c. No plus c. Where it changes or gets a little bit more complicated is if the bound isn't simply an x. So if you think about this case, it's just f of x minus f of a, where a is a constant, so like the derivative of a constant becomes what? 0. So if you wanted to see this, like, do you need to see it like the long way? Like, if you found the antiderivative, and then you took the derivative of that, why it becomes this? We're okay? We believe it? That's what I was trying to get at. So, right. So ignore that we're finding the derivative, right? So take the actual antiderivative. So the antiderivative of this would be 3t squared all over 2 plus, you can't take the antiderivative. We'll do it on the next example. Because you don't know how to take the antiderivative when there's something inside yet. But we could do it for this one. So what is the antiderivative of cosine? Sine. So you get sine of t from x squared to 2. So what do you do with that? You say, okay, it's the sine of x squared minus, what's wrong?
Ours isn't the same. It's from 1 to x squared.
Just change it to a 2 since I wrote 2 on there. Okay. The 2 and the 1 are, it's not going to matter at the end of the day. It's not. Because watch. This is your antiderivative. Take the derivative of this. So you're taking d dx to get dy dx. So what's the derivative of sine x squared? Start on the outside. What's the derivative of sine? No, you're right. Cosine x squared times 2x. What would the derivative of sine of 2 be? What is the sine of 2? And I think I changed it to a 1 because sine of 2 is outside of its actual domain. Like, do you know what I mean? Like, the domain of sine is 1 to 1, negative 1 to 1. Which is why I probably changed it, because I realized after years of typing. So, but anyways, treat that like a constant. You should get a number. So the derivative of a number is 0. So that's where like that bottom half goes. But what do you notice about this answer and had you just plugged in that upper bound? It didn't match up. Now did it? Like the little rule didn't work. If you just plugged in your upper bound like you thought you were supposed to, you would have wrote that down as your answer. So where the flaw comes in is if your upper bound isn't just an x and it has a derivative itself, you have to plug in the upper bound and then multiply by the derivative of the upper bound. So what you weren't seeing here is when you plugged in this upper bound, if you actually multiply by the derivative of x, you get 1. So that's why you weren't seeing this. So that's why I said this isn't a good example, because you can actually see why we have to take the derivative of the upper bound. So fundamental theorem of calculus says if you take the derivative of an antiderivative, you actually have to pay attention to the bound.
Well, getting it down to multiply by derivative.
Exactly. What happens if the upper bound is a 5 and the lower bound is the x? Right, we want to flip it. The lower bound has to be the constant in order to be the number minus the constant. So we're going to make it negative the integral from 5 to x of 3t sine t dt. So now taking the derivative of that, so again, that's kind of what you're saying, the derivative that? What's the derivative of your upper bound?
1, 1.
So this one's kind of nice, and you just get negative 3x sine x. What happens here? You don't have a constant now on the bottom. Think about what we did over there. We went from A to B minus A to C, right? Where A was the constant. Doesn't matter what your constant is, except for maybe possibly its domain, like I talked about the sign. So what we can do is kind of treat these like an A to B, and you want to make it so that they're zeroed out. So you almost want to do this to that. So we're going to take 0 to the upper bound. So we're going to rewrite this so that it's y equals 0 to the upper bound. I'm just going to call it f of t for the sake of writing right now. Minus 0 to the lower bound. So now I have those constants. So if you have a variable to a variable, you have to break it up so that the lower bounds are zeroed. Now you just apply FTC. So remember, all you do is take this and plug it in. So it becomes 1 over 2 plus e to the x squared times derivative of x squared minus 1 over 2 plus e to the 2x times derivative of 2x, which is 2. Good? We'll pick up with that one tomorrow to start. Your homework is actually back in our real textbook. And I actually wrote down the page number for once. Stop at 25. Because 27 is a natural log, and we didn't get to the natural log example. Yes, one last problem. So it goes 7 to 25 odds.
Okay.